Welcome to today's video. So today I'm going to be going through how to diagonalize a symmetric matrix. So basically I'm just going to be answering these four questions from exercise 1. So the first question is going to be to how to orthogonally diagonalize a matrix. The second one will be to give a spectral decomposition of a matrix. The third one will be to give a quadratic form of a matrix. And then the fourth one will be to how to change the variables of the quadratic form of a matrix, right? So I've already drafted the solutions to these questions down below. So with that said, I'm just gonna get to the solutions and explain how did I arrive to like each step. So first question, how to orthogonally diagonalize a matrix. So the first goal will be to find the eigenvalues of that matrix that we're dealing with. In this case, we're dealing with matrix A. So if you apply the process of finding eigenvalues, you'll find that your eigenvalues are 3 and 0 has a multiplicity of 2, right? So now the second goal will be to find the eigenvalues the eigenvectors associated with eigenvalues. So the first eigenvector that we're gonna find is the one that is associated with eigenvector 0, right? So remember that our eigenvalue is not supposed to be 0, right, in this case. So you do that and you'll find that your eigenvector v is supposed to be given by this. So this now basically means that our eigenspace for vector for eigenvalue 0 becomes this, is now spent by that. So now we're gonna find the eigenvector associated with eigenvalue 3, right? So we apply the same process. You'll find that your eigenvector m is given by this. So now the eigenspace for for eigenvalue 3 is now given by this. But then now we need 3 orthogonal eigenvectors because we're dealing with a 3 by 3 matrix. So to like get our 3 orthogonal eigenvectors, we need to apply the Green-Schmidt process to the eigenspace 0 then. So if we do apply the Graham-Schmidt process to the eigenspace 0, obvious our v1 is just gonna be with this first vector here, so which is just have it here, and then you're gonna apply a Graham-Schmidt process to v1 to get v2. So this means that this becomes our v2, but then now we just want to avoid working with fractions, so we just find v2 prime, which we're going to find it by multiplying v2. So now v2 prime becomes 2 times v2, which it becomes minus 1, 2, and 1. So now that means these 3 vectors are our orthogonal eigenvectors, and you can check them. All of them are like orthogonal to like each other. You can multiply this and this, you're gonna get 0. That with that, it's gonna give you 0. This and this will give you 0. So that means these eigenvectors are all orthogonal. So the following thing that is gonna need to be done will be to normalize these 3 orthogonal eigenvectors, right? So if you normalize them, you're gonna get these vectors as your normalized vector. So q1 is you're gonna get q1 by normalizing the first one, q2 you're gonna get it by normalizing the second one, q3 you get it by normalizing the third one, right? So now you're gonna have matrix q, and matrix q is actually made up of the normalized 3 orthogonal eigenvectors. So matrix q is basically q1, q2, and q3. So this column is q1, this one is q2, and this one is q3, right? And matrix D is just it's just a diagonal matrix which is made up of your eigenvectors. So remember, these were our eigenvalues, where we had 3 and we had 2 zeros. It is a multiplicity of 2. So our eigenvalues are 3, 0, and 0, which are just gonna lie in the diagonal, and then the remaining components are just 0 because this is a diagonal matrix. So now this means that our A is equivalent to Q times D times Q transposed. You can actually check this by multiplying Q times D and Q transposed. You will find out that this is equals to A. So that means you have orthogonally diagonalized matrix A. Now the second question was give the spectral decomposition of matrix A. So this is the formula to like give the spectral decomposition of a matrix, but then in general you can add this into n eigenvalues. For like instance, in general, this is the formula. But then in our case, since we just only have 3 eigenvalues, so we're just gonna have lambda 1 q1 q1 transposed, lambda 2 q2 q2 transposed, plus lambda 3 q3 and q3 transposed. So now substituting everything that we have here. So this is our lambda 1, which is we're gonna make it 3. You take it 3, and then now q1 from here, and then q1 transpose, it becomes this. And then remember, the rest of the eigenvalues were 0, so basically this whole thing just becomes 0. So you're just dealing with this thing only. So you just multiply this column and this row multiplied by the scalar 3, you're gonna get this matrix, which is matrix A. The third question was find the quadratic form Q associated with matrix A. There is basically a formula for like doing that. So the formula is given by this. So it's like, just first things, you just assume vector x to like have component x, y, and z, and then Q is gonna be given by x transposed times A times x. So now you're gonna have x vector x transposed, which is this vector. When you transpose it, becomes a row vector, and matrix A from above here, and then vector x again here, and then you multiply everything, you're gonna get this. So now this is your quadratic form Q associated with matrix A. Now going to the last question. The last question said find a change of variables to transform Q into quadratic form without cross product terms. So that means that we do not want x times y, like here. You see here we have x times y, we have x times z, y times z. So we want a transformed form that does not have x, y, or y, z, something like that. So with that said, we're just gonna get to the solution. So the first thing to like note is that D is actually equivalent to Q transpose times A times Q. Then this means that a change of variable of x bar equals to Q times vector M, where x is is this vector from question 3, and m, you just now come up with like a new vector m, and vector m has components v, w, and p, converts q into this. Now q of m is given by m transpose times d times m. See? So with that said, you transpose m, you're gonna get this times matrix d, the diagonal matrix from here, and then times matrix times vector m, and then your answer becomes 3v squared. This thing that we got here is equivalent to this over there. The only difference now is that this one does not have cross product terms. You just have a straightforward term. So that will be all in terms of answering exercise 1. And then there is exercise 2. Should you wish to like answer it, you can take an exercise and answer it, and if you struggle, you can comment below. I'll gladly reply to your comment. And if there's anything that you didn't understand, do comment below and I'm gonna reply to you as soon as I can. Thank you for tuning in to my today's video.